Alright, so in this video I'm going to talk about the surface area of a surface and also talk about a surface area of a graph, of a function. Alright, so let's start with what we learned in 16.6, in which we defined a surface using a vector valued function, r, multivariable, parameters u and v, in which you've got scalar function x, multivariable function here of uv, y is a function of uv, and then you've got z as a function of uv. And this forms some sort of surface, right? So this is a function of a vector valued function of a surface. And what we want to do is be able to find the surface area of that surface. And that is detailed in definition 6 on page 1117. And I'm just going to go ahead and write that. So your area of your surface is the double integral of the magnitude, right, of partial r with respect to u and partial r with respect to v dA. Great. Now we know that partial r with respect to u is just going to be that partial x with respect to u, I plus partial y, right, j plus partial z with respect to k, and then so now you've got partial r with respect to u and then your partial r with respect to b. So you've got x, partial y, partial, and z, partial with respect to v. All right. So that's what these two are, right? And you're going to end up doing the cross product of the two. And there's a couple examples in the book, starting on page 117. So you can go through those. Then you're going to find the magnitude. Now, and that should be pretty straightforward. We've done double integrals. You can do the magnitude and cross product of the partials. Now, we're going to move on here. And so this is definition 6. So I'm actually going to box this for you so we know what we're talking about here. So there's the area of that surface. Now suppose we have this special case where we have a function of a graph and a function of a graph here. Right, a multivariable function of a graph. And we want to find the area of that, right? So to do that, we see here that, first of all, our parameters we can set as x and y themselves. So if that's the case, we can just say, well, x is going to be defined as x, and y is y. So we've got a function of x, y, x is a function of x, and y is a function of y. So it becomes pretty straightforward to say that your r, right, your r is going to have the parameters x, y this time. All right, and that, right, so you could okay, so let's just do it this way. So you've got some sort of function x, which is x, and this is y, which is a function of y, so it equals y. So, and then we just got a function of x, y. All right. So you see the difference here in our original parametrization of the surface and the parametrization of this graph f of x, y. So now that we have this, and again, this is just a special case, right? We're doing basically the same thing, but this becomes a little bit simpler once we have that graph. So we go ahead and we plug this into our definition 6. So we take the partial r with respect to u, cross it with partial v, partial r with respect to v, and find the magnitude, and then you do the double integral. What you'll end up with here is, inside that double integral, the square root of 1 plus dz dx squared plus dz and dy squared dA. So now you end up with this area formula, and that's definition 6. That's definition 9. That's definition 9 on page 1118, and you can see how they defined that on that page. So you can walk yourself through that. Now, I definitely want you to memorize your definition 6. You can go ahead and memorize definition 9. Otherwise, if you do have a function and you go through the process using definition 6, you're going to end up here anyway. So no need to really memorize definition 9 unless you want to save yourself a few seconds in doing that. That is it.